So I'm going to come back to the Roy's identity. So let's go back to finding the Marshallian demand. Yes, the marginal rate of substitution was minus MUX MUY. So once again, this is the utility function. Don't forget the minus. MUX is 1/2 x to the power minus 1/2. MUY is 1. So therefore this is minus 1/2 squared of x, correct? And then MRS equals price ratio minus price ratio basically implies, minus this equals PX over PY minus, don't forget, so they are plus. So that means PY over 2PX equals square root of X. Hence, X is equal to PY squared 4PX squared. Okay, so that's the first mistake. Let's correct it. PY squared divided by 4PX squared. All right. Well, given this, what is the Y, the optimal Marshallian demand Y? Well, XPX plus YPY equals income. I'm using the budget curve again. So whenever I see X, I'm going to plug this. So I'm going to have PY squared divided by 4PX squared times PX plus YPY equals M. So this PX squared and PX will cancel out. So I send everything to the other side except YPY equals M minus PY squared divided by 4PX. So once I divide both sides by PY, Y is equal to M over PY minus PY over 4PX. Okay? So M over PY minus PY over 4PX. Fine. Well, that's going to change the indirect utility function, I believe. So let's do the indirect utility function. So the indirect utility function V Px Py income is equal to square root of x, which is square root of Py squared 4Px squared plus y itself, which is M over Py minus Py over 4Px. There you go. So Py over Px term will not cancel out this time because this is Py over 2Px plus M over Py minus Py over 4Px. So that means this is M over Py, this term, plus 2 times this. So that means Py divided by 4Px. So it's M over Py. So V Px Py income equals M over Py plus Py divided by 4Px. All right, there you go. So small mistake leads to a snowball effect, and the rest of the question can be wrong, unfortunately. So be careful. Should be very careful. All right, so let's come back to the Roy's identity. I don't need this. So the Roy's identity again is these two guys. So let's verify it. We're not proving it, we're just verifying it. So minus, what is the partial derivative of this guy with respect to Px? The first term's derivative is going to be 0 simply, plus the second term's derivative is minus Py divided by 4Px squared. All right, well, let me be careful. So how do we, probably this is wrong. So when we take the derivative of this guy, Py divided by 4Px with respect to Px, so the derivative of first part with respect to Px, which is 0, minus derivative of the second part with respect to Ps, 4, divided by square of this guy, right, 16Px squared. So therefore, oops, don't forget the minus. So this 4 and this 16 will cancel out. So this is going to be minus 1 times the second Py, I forgot that one. So it's minus Py divided by 4Px squared. So apparently that was correct. Okay, divided by the partial derivative of the indirect utility function with respect to M it's easier because this term doesn't depend on m, so its derivative is 0, but this term is nothing but 1 over py. So what do I have? I have here minus minus, so it's going to be plus py divided by 4px squared times, instead of writing 1 over py, it's just py, right? So that's equal to py squared divided by 4px squared, which is, as you see, x relate. All right. Well, what about verifying the Roy's identity for good y? Well, what is the partial derivative of the indirect utility function with respect to py? Well, it's equal to, don't forget the minus sign, minus m divided by py squared plus 1 over 4px divided by partial derivative with respect to m, it's just 1 over py. All right, so here I have, so here I have minus minus plus m divided by py squared times py minus plus minus 1 over 4px times py. So if you sort of simplify it, this py and py squared will cancel out. So it's m over py minus py divided by 4px. Okay? Which is exactly what the Marshallian demand is for good y. All right, guys? So that basically means if you don't know the Marshallian demands, you can actually recover the Marshallian demands if you know the indirect utility function by simply taking sort of calculating those partial derivatives. Any question? All right. So the third part was, I believe, let me check, is find the Hicksian demand functions for good x and y. All right. Let's find the Hicksian demands. So the Hicksian demand, let me change this marker. So the Hicksian demands for good x and y, well, some textbooks use XH, YH notation, indicating the Hicksian demand. Some textbooks use CC, sort of XC, YC, meaning compensated the demand, all right? Well, to be honest, I don't really care about the notation you use, but I mean, don't use any other letter, all right? Sometimes I may use, or some of my notes may use XHYH, some of them may use XCYC. That basically means the Hicksian demand or compensated demand, means the same thing, okay? Oops, sorry. So how do we find the Hicksian demand? Well, the Hicksian demands solve the following optimization problem. To minimize the expenditure by choosing x and y in real numbers. What is the expenditure? Well, it's basically xpx plus ypy, right? That's the expenditure. Obviously, income is not part of expenditure, right? You don't spend income. I'm sorry, it's not part of expenditure, yeah. So the minimized expenditure, subject to, you would like to achieve certain utility level, greater than or equal to u bar, let's say. But because the utility function is an increasing function, you don't really have to write greater than or equal to, it's just write u bar, okay? Well, how do we solve the Hicksian demand? Well, simple, write down the Lagrangian. Write down the Lagrangian and we are going to, so what is the Lagrangian? As always, the objective function, in this case, it's xpx plus ypy, all right? And then, well, let me be clear about the exact notation and I will tell you why. Okay. So I'm going to say this is plus lambda u of xy minus u bar. All right. Well, you'll see in some textbooks, they do not write the Lagrangian exactly this way, but they do write the Lagrangian this way: xpx plus ypy minus lambda hold on a second. Yeah, u of xy minus u bar. Okay, or even, well, I mean the same thing. Yeah, let me write it. L prime, let's say L double prime minus xpx plus ypy plus lambda u bar minus u of xy. All right, so probably you realize that it really doesn't make much difference whether you solve this optimization problem by using this Lagrangian or this Lagrangian or this, because, you know, this guy L prime is nothing but minus L. Same here, this is also equal to minus L. All right, so basically I am just multiplying this entire functional form with a minus sign. All right, and here I'm just taking this minus to inside the parentheses. So whether you maximize this or maximize this is not making any difference, partly because we are looking only on the first order conditions, meaning the first order condition for this Lagrangian and this Lagrangian will be the same. And therefore, most of the times we're not really looking at the second order conditions, partly because our utility functions are nice enough. And so the first order conditions are going to give us both the necessary and the sufficient conditions. So we don't really check the second order conditions. And so it really doesn't matter whether you calculate the first order conditions by using this Lagrangian or the other two. They will be the same. But as I said, some textbooks use this or this. Partly because it says, look, if you are minimizing a function, it actually kind of maximizing the minus of it. You see what I mean? So if I have a function f of x that I like to minimize, that means you multiply this f function by minus x and then maximize it. And so whatever the value you find here is going to be, so this is the minimum that I want to do, and then maximize this minus thing. So sort of that's the idea. Why those others, I mean, some textbooks use, you know, these other two Lagrangians. Okay? Any question, guys? Okie dokie. So, don't forget our utility function is, I am not rewriting it, it's this minus u bar. So if you find the first order conditions, del L, del X, del L, del Y, and then finally del L, del lambda. So, which is, the partial derivative with respect to X is sort of simple. Here it's just Px. Here it's plus lambda over 2 x to the power minus 1/2. That's it. Equals 0. Here, the partial derivative with respect to Y is Py plus lambda equals 0. And then partial derivative with respect to lambda is just going to give me the square root of x plus y minus u bar equals 0. I have three unknowns, x, y. Y isn't even there. I have two unknowns. Y is here. So I have three unknowns, x, y, and lambda, and three equations. So I should be able to solve x, y, and lambda. But to be honest, I don't really care about the value of lambda. All I care is x and y. So how do we find it? Well, simple, rewrite everything. So this is px equals minus lambda over 2 square root of x. So this guy means py equals lambda. And, this is just the constraint. My utility, it should be at least u bar. So square root of x plus y is equal to u bar. All right, so from these two, I can actually solve x, right? By the way, this is also minus. Today, for some reason, I'm making too much mistake. I don't know what's wrong. All right, so how can I solve it? Well, I mean, simple. Whenever you see minus lambda, just plug py, right? So that equals px, that's equivalent to px equals py divided by 2 squared of x. So that means x equals py squared, divided by 4px squared. Are they the same thing? Yes, they are. I mean, is this if I didn't make any mistake? So the Hicksian demand and the Marshallian demand for good x are exactly the same. All right, good. How do I find y? Well, y is going to be different because remember here I was finding y by inserting x into the budget line and then solving y. Here, however, I'm going to be inserting x into not the budget line, but this equality, this constraint. And so the y is going to be different than this one. Well, how so? Well, whenever you see x, just plug py squared divided by 4px squared, which basically implies square root of this thing means py over 2px plus y equals u bar. Hence, y is going to be u bar minus py divided by 2px. All right, so this is Hicksian demand for good x, so xh, and this is the Hicksian demand for good y, yh. Okay, any question? All right, so now what I want to do in the fourth part, I guess, what is the expenditure function? Well, by the way, let's note them here as well. xh is equal to py squared 4px squared, and then yh is equal to u bar minus py divided by 2px. Good. Now I said, what is the expenditure function? So remember, the expenditure function is xpx, x times px plus y times py. So those x and y's are not Marshallian demands, those are the Hicksian demands that you should be using if you want to find the expenditure function. So the expenditure function, denoted by E, capital E, small e, doesn't matter. It should depend on price of good x, price of good y, and the utility level you pick, u bar. Some textbooks use u0 instead of u bar. I don't mind. Again, which notation you use. So this is x Hicksian times px plus y Hicksian, times py. So what is the Hicksian demand for good x? We already found it. Py squared divided by 4px squared times px plus, what is the Hicksian demand for good y? Well, it's the u bar minus py divided by 2px times py. So all I have to do is just simplify things. Well, this is going to be u bar times py minus py squared divided by 2px plus, this px and px squared will cancel out, py squared divided by 4px. So don't forget, this is 2py squared divided by 4px. So that means this is minus, this is plus. So I'm going to have u bar py minus py squared divided by 4px. Or take the py parentheses, u bar minus py divided by 4px. I mean, I'm just rewriting it. All right, so this is the expenditure function. So also, let's put it here, py parentheses, u bar minus py divided by 4px. Okay, so the next question was, find the expenditure function and verify the Shepard's lemma for good y. Okay. So what is the Shepard's lemma? Well, the Shepard's lemma, sort of, similar to Roy's identity. It says you can recover the Hicksian demand by calculating the partial derivative of the expenditure function. And in fact, it says the following. The Hicksian demand for good y should be equal to a partial derivative of the expenditure function, and there's no minus sign with respect to the price of this good, py, okay? And so remember, this is the expenditure function. If you take its derivative with respect to py, it's equal to u bar minus py squared. Its derivative is 2py divided by 4px. So it's nothing but u bar minus py over 2px, which is exactly the same as the Hicksian demand. All right? So yes, the Shepard's lemma does hold for this question. Well, the Shepard's lemma and the Roy's identity, they're always true if the Marshallian demand and or the Hicksian demand are differentiable, obviously. If the demands are not differentiable, clearly we can't really take the derivatives, and hence for that reason Shepard's lemma or the Roy's identity would not be valid. But otherwise, whenever you have x, the Hicksian demands and the Marshallian demands as a sort of continuous functions, well, they will always be continuous and differentiable functions, they will always be valid lemmas or identities.